Hello friends. So today we are going to solve 2016 advanced question. So in the first one, a conducting loop in the shape of a right angle isosceles triangle at a height of 10 centimeter is kept such that 90-degree vertex is very close to infinitely long conducting wire. See the figure. The wire is electrically insulated from the loop. The hypotenuse of the triangle is parallel to the wire. The current in the triangular loop is in the counterclockwise direction and increased at a constant rate of, this is 10 ampere per second. Which of the following statements is or are true? So this is basically multi-correct question. So we are given a figure in which we have a isosceles triangle and there is a long infinite wire, and we have to, with respect to, and the current flowing through the wire is counterclockwise and it is increasing at a rate of 10 ampere per second. So as the current is increasing, so that we can say that the rate of change of the current in the loop is anticlockwise, and triangular loop is counterclockwise. So we can say the rate of change of current in the loop it is given as counterclockwise, and we can say from here that di upon dt is our 10 ampere per seconds. So let us consider a small strip which somewhere here the thickness of this strip is dy, and the width of the strip is such that on the either side of this vertical line, the strip length is rather y on the both sides. So total length of this strip comes as 2y. And from the long infinite conductor, this height or the distance is also y. So let us call this as A, this as B, and we have C, and we can call this as midpoint from here D. This is our E, and another point is called as F. So we can write that, let us consider considering a strip of thickness dy at a perpendicular distance y. Therefore we can see, or rather we can say that the triangle EDC, EDB, okay, is also isosceles. So you can say triangle EDB is nothing but our isosceles triangle. And Therefore, like we have written, we can write the ED is equal to DF is equal to Y. So we have here, based on this isosceles triangle, we can write ED is equal to DF, and this will be also equal to our BD, and this entire is equal to Y. Now we can write that magnetic flux due to a straight wire. Magnetic flux due to a straight wire, and that can be written as d phi is equal to B multiplied by small area dA, where B is the magnetic field due to straight wire and dA is the area of the strip. So we can say B is equal to magnetic field due to straight wire and dA is the area of the strip. Therefore, we can say that our d phi will be equal to, we know already our B, and this B is equal to mu naught I upon 2 pi Y, and our dA, that is area of the strip, will be equal to thickness of the strip and its length. Length is 2y and thickness is our dy. So we substitute both values, we get this as mu naught I upon 2 pi y multiplied by 2 pi multiplied by dy, and here this 2y cancels out and this comes as our mu naught I upon pi and multiply by dy. And now we can consider the whole, you can say the complete area, and the limit is from, you can say 0, and this is 10 centimeter, which can be written as 0.1 meters. Therefore, we can say that total flux, which will be our phi, will be integration of d phi, and this comes as mu naught I upon pi, and integration from 0 to 0.1, and we have our dy. Now it's a simple integration. We get our flux phi is equal to, this comes as mu naught I upon 10 pi. Now if we differentiate this equation, we can say differentiating, we get d phi by dt is equal to mu naught 10 pi, and we get our di upon dt, and rate of change of current is given as 10. So we substitute it here, we get mu naught 10 pi multiplied by 10, and this 10 goes with 10, we get mu naught upon pi. Therefore, in the option, that is, we have to find out the induced EMF in the wire is nothing but mu naught upon pi. So option number C is correct option. Or from here, let me write it here, I can say my induced EMF is equal to mu naught upon pi. So therefore option C is correct. Okay, now next it is said that we are going to check all the options now, and in the option number A, it is said that there is a repulsive force between the wire and the loop. So let us understand the magnetic force between nothing but parallel current carrying conductors. Magnetic force between parallel currents, and we already know this concept. Then when the two parallel currents are in same direction, they are going to repel each other. Okay. So let me write here. So we can say that two parallel currents in same direction repel. And the induced current in the wire is in the same direction as the current in the hypotenuse. So you can say induced current in the wire is in same direction as the hypotenuse, and that hypotenuse was, as per figure, is our AC. Same direction as hypotenuse, which is our AC. Therefore, they repel each other. They repel each other. So our option A is also the correct option. Option A is correct. And option D is automatically, you can say, as option A is correct, so option D will be incorrect, because it says that induced current in the wire is in opposite direction to the current in the hypotenuse, whereas we just found out that they are in same direction. So based on this, we can further make a conclusion that option D is incorrect. And now we are left with only one option to check that what happens if the loop rotates. That is our option number B. It says that if the loop is rotated at a constant angular speed about the wire, additional EMF of mu0 upon pi is induced in the wire. Okay, so let us rotation of the loop. Rotation of the loop. So in this case, what happens as the triangular loop rotates about infinitely long wire, it is at a constant angular speed. The flux which the flux linkages rather does not necessarily change periodically. If there is no, you can say, periodic change of the flux linkages, then we cannot claim that the additional EMF will be mu naught upon pi. Okay. So from here we can say that if the triangular loop rotates about the wire with constant angular speed, the flux linkages does not necessarily change periodically. And we can also make a, you can say, another important conclusion or point from here, that simply rotating the loop around the wire does not significantly change the mutual inductance, because the relative position of two conductors remain the same. From here also we can say that simple rotating the loop around the wire does not change the does not, let me write a word, does not significantly change, does not significantly change the mutual inductance as the relative position of the two conductors remain the same, as the relative position of two conductors remains same. So we can for sure cannot say that the additional EMF of mu naught upon pi will be induced. So we can say from here that additional EMF of mu naught upon pi is induced, cannot be justified. Therefore, this was our statement number, I think, C. The statement number C is, sorry, it was B, is incorrect. Therefore, option B is incorrect. So this completes the first one. Now we come to the second one, and second one states that we have a two inductors, L1 inductance 1 millihenry and internal resistance, this should be 3 ohm, and L2 inductance 2 millihenry, internal resistance is also 3 ohm, and a resistor R of resistance 12 ohm are all connected in parallel across a 5-volt battery. The circuit is switched on at a time t is equal to 0. The ratio of maximum to minimum current 𝑰max, 𝑰min drawn from the battery is. So in this case, we have, let us draw the circuit. So we have an inductor L1 having an internal resistance. So let us suppose this is L1, internal resistance R1, and we have inductor having internal resistance, and let us call this as L2, internal resistance R2, and a resistor R of 12 ohm, all are connected in parallel. And we have resistance, let us suppose that R, and all these are connected through a switch with a battery, and battery is of 5 volt, and this is a switch. L1 is given as 1 millihenry, internal resistance is 3 ohm. Okay. So in this case, we have to find out the ratio of 𝑰max upon 𝑰min. So in this condition, it is said that the circuit is switched at time t is equal to 0. So we can discuss the maximum and minimum current as you can say with respect to this switching of the switch. So we can divide it into two parts. The first we can say at t is equal to t0 positive, so which basically means just after switch on, just after switch on. And under this condition, the inductors act as open circuit. Inductor acts as open circuit. Therefore, that means the current through the inductors will be 0. Current through inductor will be 0. And the second, at t is equal to infinity, which is also called as a steady state. And here the inductors act as a short circuit. Inductor acts as a short circuit. And the current reaches the maximum value. And current reach a maximum value. So let us discuss the first case, and which is our minimum current, which we can represent as 𝑰min, and that happens at t is equal to 0 positive. So therefore, at T is equal to 0 positive, current through inductor 1, that is L1 will be equal to 0. Current through inductor L2 will be also equal to 0 because they are open circuit. And the current through the resistor, if we can write that, okay, so these two are current through inductors. Current through inductors. And next we can find out the resistor current. Which is suppose is of IR, that comes up of V upon R. V is our 5, resistance is given as 12. Yeah, it is given as 12 ohm. So our IR comes as this. So we can find out the total current. Total current, that is our I total at 0 positive will be equal to IL1 plus IL2 plus IR, and this comes equal to our 5 upon 12 amperes. So we can say that our I total at 0 positive will be equal to our I minimum, because the current starts at T is equal to 0 positive and increases with time. And increases with time. Now we can find out our maximum current. Maximum current, which is our 𝑰max, and this happens at T tends to infinity, which is our steady state. Now the inductor will be short circuit and it will be consisting of only their internal resistances. So we can say the branch current so now we are going to have 3 branch currents. The first one is L1 branch, resistance is given as R1, which is our 3 ohm. Therefore we can write that our IL1 at infinity will be equal to V upon R1, that is equal to 5 upon 3 amperes. Next is our L2 branch, resistance is our R2. So we can write our IL2 at infinity will be equal to V upon R2, and V is our 5 volt and the R2 is given as 4. This becomes, and our IR resistor will be same. So we can say resistor R, and that will be equal to IR, which is equal to 5 upon 12. Now we can find out the total equivalent resistance. equivalent resistance. All the resistance is in parallel. Therefore, we can say our R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R. And this will be equal to 1 upon 3 plus 1 upon 4 plus 1 upon 12. And this comes as our 12, and this will be 8 by 12, and which can be written as 2 by 3. Therefore, we have our R equivalent will be equal to 3 by 2. Therefore, the total current, that is our I total, but for now infinity, will be equal to V upon R equivalent. V is our 5, and this is our 3 multiplied by 2, and this comes as 10 by 3. And we can just cross verify, but that is not required. So this is our 𝑰max. We have to simply find out ratio now. The ratio is of 𝑰max upon 𝑰min. And this comes as 10 upon 3. And 𝑰min is our 5 by 12. This is equal to 10 by 3 multiplied by 12 by 5. And this can easily cancel. This 5 goes by 2 and this 3 goes by 4. And we get this as 8. Therefore, 𝑰max upon 𝑰min is equal to 8. Okay, this was an integer type question, so the ratio is our 8. So these were the two questions asked in the 2016 advance. So this completes the questions. Thank you.